Okay, 11.11 is applications of Taylor polynomials. So we're actually going to apply some things to them. One thing is how good of an approximation is it? So when we did, like, for example, sine of x. Sine of x obviously goes on forever when we write it out forever. But we know sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And we'd put like a dot, dot, dot in the back of this, right? But let's say we didn't and we just did the first 3 terms. Okay, so if I only did 3 terms, how good of an approximation do you think that is? It's pretty awful, right? It would be good close to 0, though, wouldn't it? If we look just on an interval really close to 0, we'd know it's pretty close. But the further we get out, it gets pretty awful. Okay, so that's one of the questions we're going to kind of answer here is how good of an approximation is it? And then how large would we take n to be to get the desired accuracy? So if they say that you want it to be correct to 5 decimal places, how many terms do I need to list out so that it's going to be correct to 5 decimal places? Sure, so we're just going to guess. Okay, or we can maybe do some math and actually figure it out. Okay, so look at the absolute value of the remainder. Okay, this stuff all here isn't a huge deal. Get out that little cheat sheet I gave you guys, and we're going to look at number 3 here. Okay, number 2 only works with alternating series. I don't ever use number 2 because number 3 works for everything, and you can just kind of go like this, you know, real lightly, sure. It's still like a valid thing you could do. I just figure if we can learn one of them really well, we can just use that one. So, okay, so you guys have that little cheat sheet. Okay, do you see how in the bottom of it says Taylor's inequality there? And it gives you this part on your sheet. Okay, what we're going to add is this part here. So I would just write in the back of here, when the absolute value of the n plus 1 derivative at x is less than or equal to m. Okay, this part has to be included with that part. So. Okay, part A here is something you guys have already done, so you should be able to do part A. Approximate this function by Taylor polynomial of degree 2. What does that mean, degree 2? To the second power. So how many derivatives do I need?
3 plus 2.
I need 2 derivatives, right? And then it's at A equals 8. So let's go ahead and find our derivatives. So let's just write what f of x is first. And I'm just going to write it as x to the 3rd power. So first derivative would be what? 1/3 x to the negative 2/3. And second derivative, negative 2/9 x to the negative 5/3. And that's all we need for part A. But for part B, we're going to need the 3rd derivative. If you remember from back here, it says the n plus 1 derivative. So that's why I need one more derivative than what I actually need for part A. Okay, so I'm just doing it now so that I don't have to do it when I get down to the next step here. So the next derivative would be what? 10/27 x to the negative 8/3. So let's just write a note that this is for part B, just so you're not confused. Okay, then what do I have to do with those derivatives? Plug in 8. So go ahead and plug in 8. You should be able to do all this without your calculator. What is 8 to the 1/3? 2. Okay, so when you do this, typically we would move that to the denominator. So I have 1/3, and then this is 8 to the 2/3. So what I would do instead of squaring it first, like you guys did, is I would do the 1/3 first, because we know 8 to the 3rd power is what? 2, and then square it, and you get 4, so I have 1 over 3 times 4. Either way, you get 1/12, right? So go ahead and plug it in here, see if you can get this one. That should be the last one we need. Okay, so did we get negative 1 over 144?
No.
Did you get negative 2 over 288?
We got 1 over 2.
Well, there's a negative 2 in the numerator.
Yeah, we already took care of it.
Check it again there. Okay, so we're trying to find the Taylor polynomial of degree 2, so I'm just going to go ahead and write this as t sub 2 of x. The notation there isn't a huge deal. So what would be the first thing I'd write down? 2. And that would be x to the 0 over 0 factorial, so you don't need to write that part in. And then we have plus a 12th, and that is x to the first, and then over 1 factorial. And instead of x to the first, what am I putting? X minus 8. So don't forget what it's centered around, okay? And just leave it like that. Don't distribute it through and stuff. They don't typically do anything with that part. And then minus 1 over 144. And then it's x minus 8 to the second, and then it's over 2 factorial. So instead of 144, what's this going to turn into? 288.
Why is that?
Because it's over 2 factorial, so I'm just putting the denominators together.
So it's just 2 times 144?
Yep.
2 factorial then?
Well, 2 factorial is just 2,
Oh.
because it's just 2 times 1. And that's all I need for part A. Okay, so part A shouldn't be anything that's new there. Okay, so second part, how accurate is this approximation when we're just looking from 7 to 9? So isn't it centered at 8?
Yeah.
So from 7 to 9, it's probably decently accurate, right? If I widened that, and instead of from 7 to 9, it was from like 6 to 10, what would happen with that accuracy? It would be less accurate, right? So you have to take into account what that interval is when you're actually thinking of how accurate it is. So let's write a few things here. When we're doing this, let's write what was on the first page. If, just so we have it. So if the absolute value of the n plus 1 derivative, because we'll be using this a lot, at x is less than or equal to m, then, so I'm just writing what's under that third bullet on the first page, then the absolute value of r sub n of x is less than or equal to m over n plus 1 factorial. And then the absolute value of x minus a to the n plus 1. This is just on the first page, okay, exactly the same thing. I just want to have it here so we can reference everything. Okay, so the two things that you want are what your n equals and what your a equals. So a is what from part A? 8, so we're dealing with that. And n, this is r sub n of x. This is the n plus 1 derivative. So how many derivatives do we need up here? 2. This is like what your n is here, so my n is 2. And then the other thing that we're dealing with is written right here. Okay, we're talking from 7 to 9. Okay, so let's start filling in to this part of the rule. So we're just going to fill in the numbers that we know instead of having the letters there. So we have absolute value of r sub 2 of x is I'm just going to say equal to for the moment. Okay, we'll deal with the less than part later. M over, yep. And the big thing here is finding what M equals, so that's what we're going to do next. And instead of n plus 1 factorial, what's that going to turn into? 3 factorial. Just leave it as 3 factorial, but yep, it'd be 6. And then absolute value of x minus 8 to the third. Where, and then I just write this part here. So the absolute value of, what derivative am I talking about here? The third. So f triple prime. And this is an absolute value. Usually just make them thicker. Is less than or equal to m. Now from above we know the third derivative, right? So instead of having the third derivative written there, and just as a warning, make sure you're not writing huge here, okay? Because you're going to need some room below. I know, but don't write huge. Okay, so our absolute value, our f triple prime was 10/27. And then I'm going to write this as times 1 over x to the 8/3, good. And I know that's got to be less than or equal to m. Okay, so this is the part that I'm really working with here. We're trying to find our m, yep. That's the big thing here, yep, is find what your m is. Okay, so any questions so far? I know we haven't done very much yet, just a lot of substituting stuff, so. Okay, so let's just put a little bullet here. So we're going to say since x has to be greater than or equal to 7 because of what we have here. So you always take the smaller one, say x is greater than or equal to the smaller one. Think about x to the 8/3 because of my derivative. I'm trying to find my m here. So think of x to the 8/3, how that compares with 7 to the 8/3. Which one would be bigger? Look here, x is larger than 7, right? So if the x is bigger, then this one's bigger, right? So the third derivative of x. We know the third derivative of x is this 10/27 times 1 over x to the 8/3. Think about how that compares. So we're going to fill in the blank here to 10/27 times 1 over 7 to the 8/3. It's going to be smaller. Why? Yeah, because the denominator is bigger, right? So the denominator here is bigger, making it smaller. Or could equal, yep, if it was at 7. Okay, now get your calculators, put this in your calculator, because that's just a number, right? That's not, it doesn't have any variables anymore. So, and we'll take it out to quite a few spots here. So are we getting like 0. What? 206. 5. So let's go like to there, okay? It's approximately that. Now, do you see how this is less than? We're always dealing with less thans, okay? You always want your signs facing the same direction. So I know this is less than 0.0021. That works, right? Okay, as long as this number is bigger, you're okay. So then this is going to be my m value right here. Because isn't it, yeah, or it could be like 0.00207 you could put, you see what I mean? Okay, it just depends how accurate you want it to be. Don't get like carried away going like ridiculously far, okay?
But once you get that number, you just pick a number that's a little bit larger.
Well, your m is the one that's bigger than what this is here, right? So we know that because of what we have here, this is what my m has got to be something that's a little bit larger than this.
Still close to it?
Yeah, close to it. Should be really close to it. So like I said, if we put this, that's okay. All right, you might choose something slightly different for your m. As long as it's larger than what this piece was here, then you're okay. All right. Don't pick like, oh, 0.1, because then your answer is going to be not very accurate, obviously. Just so we've got it kind of laid out. Therefore, m is, we're going to say this 0.0021. And like I said, if you use 0.00207, that's fine. This is just what I used in these notes, so I'm going to stick with it, okay? Nope, we're not going to do the 9 side. You're always just doing the smaller side, okay? That way this ends up in the right direction. If you were using the 9, this would end up with a greater than, and then it wouldn't fall under the rule, okay? Okay, so this is the piece here that I'm really like worried about, right, that I'm using my rule for. So I've got my m value. What's the other value I need is this x minus 8 value, right? So the value of x minus 8. So that's really what I'm caring about here is what my x minus 8 is. So let's put a bullet here and keep going. These are kind of the two big pieces. So since your x is between 7 and 9, so we'll kind of scrunch it like this. What we really want is x minus 8. Okay, we don't really want this x here. So how do I get this so it turns into an x minus 8? Subtract 8. So subtract 8 from each piece here. So this would turn into what on the left? Negative 1. So I've got negative 1 is less than or equal to x minus 8, which is less than or equal to 1. So then I can say that the absolute value of x minus 8 is what? Think about like the ratio test that we did, is less than or equal to 1. Okay, so now we're going to take what we had up here, this rule up here, and we're going to plug in all that stuff that we came up with. So we know the absolute value of r sub 2 of x is equal to, instead of m, what am I going to put into its spot? 0.0021. And then I've still got this 3 factorial. If you want to write 6, that's fine. And then I've still got this absolute value of x minus 8 cubed. Okay, now I know that this is going to be less than or equal to, this stuff just stays the same. And instead of x minus 8 cubed, what is it always less than or equal to? 1. So I can put 1 cubed here. Obviously, you don't need to cube it. And you would have absolute values there if it was a negative, so I'm just going to write them. But obviously, you don't need all that for this particular one. And then isn't this just a number? Yeah. So put it in your calculator. Really, it's just 0.0021 over 6. Okay, right up here, you know that the absolute value of x minus 8 is less than or equal to 1, right? So here I have the absolute value of x minus 8 cubed. That's going to be less than or equal to 1 cubed. Or the absolute value of 1 cubed, whether you have the absolute value or not, is not a huge deal for this problem because it's positive. It should always be positive, so. Do you see that? This is less than or equal to? And then when we type this in, you get what? Whoops, I should probably put approximately. 0.00035. And then we just want to have a final answer here. So everything's always less than. Do you guys notice that as we're going through? Okay, so it's less than, we could say 0.0004.
Wait, so you get .0035.
Well, what does that come out to exactly?
What are you plugging in for x?
Oh, so it's exactly. Yeah, so we could keep it like this, but if this goes on forever, just pick something a little bit bigger than it, okay?
What do you get this out?
Okay, so for this one, we could actually keep the .00035 because it was exactly .00035. If this kept going on forever, you just pick something that's a little bit bigger than it because it's a less than symbol, okay? So this would be fine, or if you round it up, that's okay. Okay, what this tells us is what our approximation in part A is accurate to. So this Taylor polynomial is accurate to within .00035 of what it actually would be at its furthest away spot. Okay, so it's not going to be further away than .00035 of what it should be from 7 to 9. So it's probably going to be at like a 7 or at a 9 where it's going to be that far away. Okay, but it will never be more than that far away. So it's just showing you how close it is what these problems do. Okay, so let's write this out so that we have it in our notes. Okay, so therefore, if our x is between 7 and 9, the approximation in A is accurate to within, and let's write this one instead. I like that number a little bit better, 00035. It's a little more accurate. We don't really need to do this in this case. Yeah. Okay, so this here is a decent approximation. The thing that's funny about this that you guys are realizing is, okay, we have to use our calculator to do this, right? And our calculator can come up with a better approximation. Let's go into your y equals, so get your calculator. In your y1, let's put the x to the third power. That was our original function. And in our y2, let's put that Taylor polynomial that you came up with in part A. And we're going to look at it from 7 to 9. So I'll give you guys a minute to get those in there. Okay, so I'm putting this in my y1, I'm putting x to the third. In my y2, I'm putting in that Taylor polynomial. Okay, now go to your table, guys. I need you to focus for just a minute. Okay, in our table, if we go at x equals 7, let's look at x equals 7. Go to your table. It should have both of those into your table here. And if we scroll, do you see how close these y values are? How could you find how far off it is? What could you do with those two y values? Subtract them, okay? And then couldn't we do the same thing at 9? So I'm just going to go by 1 so I can see both of them at the same time. So you could do the same thing at 9 because the further away you get, the less accurate that approximation is. So I would check at those endpoints, and you could do the same thing here and subtract those y values. Okay, when you do that, you would actually get at 7 an error of like 0.000263. And at 9, it's like 0.000223. So do you see how your calculator gets it more accurate than what we got it? That doesn't mean our answer is wrong. We're saying that it's accurate to within that much. Could it be even closer than what we got? Yeah, yours should be a little bigger than what the calculator gives you. Otherwise, you did something wrong. Yeah, that's not what they're going to ask you about, but yes. Yep.